You have it. The planet Vulcan, a planet of fire that was nothing but smoke and mirrors. A yearning for something, but never a reality. Newtonian physics were replaced by Einstein's theories of relativity. And now special relativity is here to stay, at least until it is supplanted by something even more comprehensive. Have you ever looked up at the sky and seen something so strange it made you wonder if you were dreaming? Perhaps you saw what looked like a rainbow, only it was upside down. Or maybe you saw a perfect circle of light around the sun with 2 splashes of rainbow color on the sides. Well, no need to pinch yourself. What you are seeing is a unique category of optical phenomena called ice halos. Although similar, they aren't technically rainbows, but their own distinct wonder. Some are relatively common, while others are extremely rare. As you might know, rainbows occur when sunlight is refracted by water, droplets suspended in the atmosphere. When light travels from one transparent substance to another, such as from air to water, its speed changes, bending its path and separating the light into colored bands by wavelength. A process called dispersion. But what happens when light hits water particles that are made of ice, rather than liquid water? Well, depending on the shape and orientation of the ice crystals, as well as the direction of the light hitting them, they can produce a whole range of optical phenomena. To date, 119 kinds of ice halos have been categorized, and they might still be others we don't know about. So what are ice halos? How do they form, and what should you look for if you want to see one for yourself? And finally, are they a sign of something more ominous on the horizon? I'm Alex Milan, and you're watching ASRAM. Join me today as we look at spectacular images of some of the better-known ice halos and get to the bottom of how and why these delicately beautiful spectacles appear. This stunning photograph shows a 22-Ag solar halo spotted over Gross-Kottenberg, Germany. 22 Ag doesn't refer to temperature, but to the angular radius of the halo. To visualize this, imagine drawing a direct line from a point on the halo to the observer's eye. Then do the same from the sun of the circle center to the observer's eye. The angle between these two sight lines is 22 Ag, hence the name 22 Ag halo. There are also 46 dihalos, which, as you might guess, are larger than their 22 Ag cousins, but are also fainter. Halos can also occur in moonlight. As you see here, these highly beautiful halos are called moon rings or winter halos, but they're technically the same. Optical phenomenon. What distinguishes them from solar? Halos is the source of light in some images. You may notice that the patch of sky inside a halo appears darker than the sky outside the ring. A dramatic effect that is sometimes described as a hole in the sky. This happens because when light bounces and refracts off the ice crystals, none of it is reflected toward the light source, which to an observer leads to an apparent darkening inside the halo. But this is just the tip of the iceberg, because ice halos take on all kinds of strange and shocking forms. Spots of vibrant color, upside down, rainbows, and even upside-down rainbows at night. But before we get there, let's take a moment to break down the fascinating optics that produce these strange occurrences, most circular. Halos are made by water crystals in cirrus or cirratus clouds. These clouds occur high in the troposphere, usually 5 to 10 kilometers above the Earth's surface where temperatures are very cold. As a result, halos can be seen anywhere on Earth all year long, even in very hot climates. Atmospheric ice crystals are small, usually less than 10 micron long, and uniform in size and shape. This extreme regularity has to do with the structure of ice on a molecular level, and is necessary for making halos. You see, water molecules consist of 2 hydrogen atoms and an oxygen atom in liquid water. The bonds between hydrogen atoms are weak, so the bonds are constantly breaking and reforming as the molecules slip past each other. But when water freezes, that molecular movement slows to a halt, and the bonds between hydrogen atoms become fixed. This results in a hexagonal lattice structure known as a tetrahedral arrangement. This highly organized structure on the molecular scale is what causes the ice particles to form hexagonal crystals. Some crystals are flat like plates, whereas others look like columns with a hexagonal cross-section. Despite this variation, these crystals behave so uniformly because of their interfacial angles. In fact, the angles between any two faces of ice crystals are completely identical. It's this extreme regularity of the interfacial angles rather than the crystal's mass or shape that allows millions of particles to scatter the light with the consistency needed to produce a halo. Halos are sometimes quite colorful. That's because when ice crystals refract light, the red and blue frequencies bend slightly different angles and disperse some 22 Adair halos, have two colorful spots visible to the left and right of the sun. These beautiful-looking phenomena are called parhelia or sundogs. Sundogs appear when ice crystals that are shaped like hexagonal plates take on a horizontal orientation. As I mentioned earlier, some crystals form as thin, hexagonal plates, whereas others form as columns with hexagonal cross-section. When plate-shaped crystals form and settle downward, atmospheric drag orients them horizontally with the z-axis. You can see pictured almost perfectly perpendicular, larger plates tend to wobble just a bit more than smaller ones. This wobble, in turn, affects how tall sundogs appear to be, with wobbler plates causing the sundogs to appear more vertically stretched. Suns are sometimes accompanied by another object, ical phenomenon called a circumzenithal arc. These arcs look similar to rainbows, only they're upside.